Hello geometers. Today we're going to take a look at some questions from section 6.2. Deals with similarity in triangles. What I have right here is question 6.2.6 all set up and ready for us to go. So when we have two similar triangles like LNM and RST, what we want to do is, the important thing about them is that the sides are proportionate. That is to say, the ratio between this side, NM, and this side, TS, is the same as the ratio between this side, LM, and this side, RS. So, let's go ahead and write that out. NM divided by TS, that ratio is equal to LM divided by RS. So numerically we would have 3 divided by 18 is equal to 1 divided by the value that I'm calling x sub 1. In the book it's just a question mark. And when you simplify this out, you get x sub 1 is equal to 6. Awesome. So we've found one of the values that we're looking for. We'll go ahead, we'll fill it in here. 6. Next, we've got two more to find, and I'm actually going to do this one next, x3. So, we don't have proportionality here, but we do have that it's a right triangle. x3 is equal to Pythagorean theorem time 3 squared plus 1 squared. Take the square root of it. That's the square root of 10. Finally, we can do the same thing with this x2, or we could use a ratio to find it. I'm going to use a ratio. x2, this side, TR, is the same as n divided by L, or NL, this side. That's the square root of 10. And that's equal to the ratio between, we'll go with RS and LM. Oops, let's actually write those numbers in there. 6 divided by 1. So then we multiply both sides of this equation by this denominator, square root of 10, and we get that x sub 2 is equal to 6 times the square root of 10. Perfect. And that's that problem solved. Next problem. 6.2, number 8. Same setup as before. We've got two similar triangles. In this case, ABC is similar to DEC. And we've got some sides marked. We're looking for the unknown sides. Now, in the book, there's just a single question mark right about here. It's in this area. That was a little ambiguous. I didn't know what length they were talking about. So I figured that because they probably wanted you to find a lot of lengths, they were talking about this one right here. Length AD, excuse me. This one right here, length AD. Figured that's what they were looking at. So to find that, we're going to have to find these two other lengths, AC and DC, and then use a little subtraction. But before that, let's find AB. AB, length x1, is to DE, length 3, as BC, length 15, is to EC, length 5. So the length of x1 is 9. This simplifies to 3. Multiply by 3, we get 9. Okay, we'll go ahead, we'll write that in there just in case we need to look at anything later. So, oops, I wanted this in a different color. 9, we just found that. Next, I know I'm going out of order on this, I'm terrible. I want to take a look at this length, x4, because I'm looking at this. I see a right triangle with sides length 3 and 5. Well, Pythagorean triplet that I know best is 3, 4, 5. So that means x4 is of length 4. Little Pythagorean theorem there. Alright, that leaves us with x2 being the next side we can find. Now, we could use the Pythagorean theorem over here, but let's be honest, squaring things is hard. So we'll set up a proportion. And since 15 and 5 divide out, that's going to be the other side of it. X sub 2, AC, is proportionate to DC. So x sub 2 over the length of DC is equal to BC, length 15, over the length of EC, 5. X sub 2 is equal to 12. One last line to find, and it's this one, AD. We can find that length, so we may as well. Now, AD was equal to, let's see here, it's AC, the long line, minus the length of the short line, DC. And that little subtraction is going to get us 12 minus 4 AD, or x sub 4 as I called it, excuse me, x sub 3 as I called it, is length 8. Alright, another one solved. Next, we're going to take a look at question 6.2, number 22. Now, in this question, we said we're told to take two similar triangles. So we're given, we are given that triangle ABC is similar to triangle DEF. And we have to prove that the altitudes of these two triangles are proportionate as well. So let's go ahead and we'll draw in some altitudes. Since we're drawing this, we're going to do it in a different color. We'll draw in some altitudes here. Remember, these guys are altitudes, so we'll make them right angles. And finally, we need to label them. So this will be, looks like we're at G, and this will be H. Okay, so the proposition that we have to prove is BG is proportionate, or excuse me, divided by EH. The ratio between BG and EH is the same as the ratio between, and the textbook just says, their sides. When you're talking about an altitude, the side of that altitude is the side that it's perpendicular to. So in this case, it would be BG is in this triangle ABC, so the side of BG is AC. And then the corresponding side is DF over here. Okay. Well, let's get to it. Here's our proof. Oh lordy, well this is the similarity section, so we're gonna have to look for some similarity. You know, if these triangles are similar, then this angle is congruent to that angle. And then I have two angles congruent to two angles. I've got similar triangles. Let's go with that. We'll see where it takes us. So that was angle BAG is congruent to angle EDH, and that's because triangle ABC is similar to triangle DEF. Similar triangles have congruent angles, however you want to state that. Next, BGA and EHD, those altitudes right here, BGA, EHD, they're congruent because they're right angles, and all right angles are congruent. So angle BGA is right, angle EHD is a right angle as well, and this is because they're altitudes. So that's the definition of an altitude for both of those. And then that means that they're congruent. Angle BGA is congruent to angle EHD. We'll use both right angles for our reason there. So this implies that triangle BGA is similar to triangle EHD. And this is angle-angle similarity. Remember, BGA, EHD, and we had 1, 2 angles similar, so those triangles are similar. That means that we can find some ratios here. And we're interested in the altitudes. We're interested in BG and EH. Now my first thought when looking at this was I could say, okay, BG over EH is the same as AG over DH, and just use the two legs of this triangle, then prove that this little triangle and this little triangle are similar, and prove that this side is proportionate to this side and this side and this side. And that just started to get way too complicated, and I said, you know what, I'm going to have to do some addition with fractions there. So I got a better idea. I'm going to take this side, BG, and say BG over EH is equal to AB over DE. I'm going to use this leg and the hypotenuse. Why the hypotenuse? Because it's part of the overall triangle ABC and the overall triangle DEF. So BG divided by EH, that ratio is equal to the ratio between AB and DE. And this is by similar triangles. Next, remember how we were given that triangle ABC and triangle DEF were similar? Yeah, well, if they're similar, then that means that the side AB over DE, that ratio is equal to the ratio of AC over DF. This is by similar triangles. This was given to us. And this one we proved. So this was proven versus given. Let me highlight again the sides that I'm talking about. AB is to DE as AC is to DF. That's what we want. This is what we had in red. Look, the red and the green overlap over here. That's the transitive property in action. A is equal to B, B is equal to C. That means that A is equal to C as well. The ratio between BG and EH is equal to the ratio between AC and DF. Transitive. One of the best properties. And then we're done.